Hello students, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in the last session of thermodynamics and KTG, so we discussed the concept of CP and CV, and also we introduced so what is internal energy, what is work done, and what is heat, and combinedly these three, so we discussed the first law of thermodynamics, right? So that's what we discussed in the last class. So today lecture number 3, so where we are going to do some questions on the first law of thermodynamics, and then the types of thermodynamic processes like isobaric, isochoric, isothermal, and adiabatic processes. Okay, chalo. So hope you guys have already done in chemistry. So here we are not going for the derivations. So what are the important points that you have to remember, and so what kind of questions they are asking in the previous year questions. So all these things we are going to focus. Our main objective is to clear the competitive examinations. So whatever that are unnecessary, I'll leave them. So what is that is necessary for us, I'll definitely keep it in the lecture. Okay, so as usual, I just need your attention for the next 1 hour, guys. Just be with me, avoid all the disturbances around you for the next 1 hour, and at the end of the lecture, it's very important to prepare your own short notes. Chalo. So the competitive examinations are around. Those students who are in class 12th are droppers. So you guys should speed up your preparation. You know how much value this period is, right? So it adds lot of marks for you if you properly utilize this period from October. Now it's October, right? October, November, December, January. So if you utilize properly this period, so it adds lot of marks for your final examination for sure. Okay, chalo. So let's get into the today's topic, guys. So let me deal with some questions first. So try to understand the given questions. So the questions are long, but the answers are easy. So just have a look at the question first. A thermodynamic process is shown in the figure. The pressure and volumes corresponding to some points in the figure are PA and PB. Values are given. VA and VD are volumes are given. So in process AB, fine. So 600 joules of heat is added to the system in the process BC, fine, and 200 joules of heat is added to the system in AB. 600 joules of heat is added. In BC 200 joules of heat is added. Okay, from here to here and here to here. So the change in internal energy of the process AC is. Try to understand the given question first. So what they gave, they are asking what is the change in internal energy from A to C. Okay, so they gave, so in AB 600 joules of heat is added, and in BC 200 joules of heat is added. Okay, so overall how much heat is added from A to, in the process A to B, and from B to C, A to B and B to C. So the total heat that is added is 600 joules plus 200 joule, so which is equals to 800 joules of heat is added. Okay, so then what I will do is I need the internal energy from A to C. So the internal energy is a state function. Either you take from ABC or you take from AC, it's going to be same. So the internal energy from ABC to, so the internal energy in AC will be same. So I know the total heat given in AB and BC. So can I find the work done under ABC? If I find the work done under ABC curve, so then I know the delta Q, I know the work done. So I'll get the internal energy in ABC. So that internal energy in ABC is nothing but the internal energy in AC path, right? Chal. So now what is the work done? The important thing is, so the work done, so the work done in ABC, so that is nothing but, so this total area, not the cyclic, so the total area under ABC. So here I could see that, so the total length is what, width is what, see here values values are not added. In the next slide, let's see. So okay, here in the question it is given. Okay, so PA is given, PB is given. So what is PA? So let's write the values here. PA it is 3 into 10 to the power 4, and then PB it is 8 into 10 to the power 4. Fine, chalo. So VA is 2 into 10 to the power minus 3. Here it is 2 into 10 to the power minus 3, and then this is 5 into 10 to the power minus 3 VD. Chalo. So now I can solve it easily. So what's the total work done? So the area under curve. The area under curve. So what is the area it is given? So let's do it in the next slide. So better. So let's write it in the next slide. So what is the area? So the total length and the total width. So this total length is how much from here? From here to here. The total length is 8 into 10 to the power 4, guys. Yes or no? So the total length is 8 into 10 to the power 4 into. So what's the breadth? So this much AD. So what is AD here? 5 minus 2, which is 3 into 10 to the power minus 3. So I can write 3 into 10 to the power minus 3. Done. So now easy. So 8 into 3, 24 into 10 to the power 1. So which is nothing but 240 joules of work under ABC. So now you got the work done in ABC, and we got what is the total heat in ABC. What is the delta Q in ABC? So 600 plus 200, 800, right? So then use the first law of thermodynamics. What's the first law of thermodynamics says? So the delta Q in ABC is equals to the work done in ABC plus the internal energy in ABC. Chalo. So the delta Q is 800. So which is equals to work done in ABC. How much we got? So 240 joules, right? Plus, so the internal energy in ABC. So done, guys. So just calculate. So the delta U. So the delta U in ABC is equals to, so 800 minus 640. 240, sorry. So 600, 560, right? So 560 joules is the correct answer. Is it there? Yes, option 1. So the 560 joules is the correct answer, guys. Understood? Clear, everyone? Chal. So let's move to the next part. So the note, so the delta U is equals to kinetic energy of the molecules, which is equals to N into F by 2 R delta T. So valid only for the ideal gases, guys. Okay, so the delta U depends on delta T, so valid only for ideal gases. You know that for the change in internal energy we have only one formula. So what's that? So F by 2 into NR delta T, or you can also write it as, so let me write NR. So N into F by 2 R, let's write this way, into delta T. So here N into, so this F by 2 R is nothing but CV. So CV delta T. So this is the only formula for the internal energy, right? Chalo. So this is valid only for the ideal gases. Now except ideal gas, if some other gas or liquid is mentioned, so then how to solve the questions on first law of thermodynamics in such cases? Let's see this question. So first understand the given information. 1 gram of water of volume 1 centimeter cube at 100 degrees centigrade is converted into steam at the same temperature. So at 100 degrees centigrade the water is converted to steam, right? So the latent heat of vaporization. So under the normal atmospheric pressure, so the atmospheric pressure which is 10 to the power 5 Pascal, that means pressure is constant. So the volume of the steam formed equals to 1671 centimeter cube. If the specific latent heat of vaporization of the water is given, so 2256 joule per gram. So the change in internal energy. So try to understand the given question. First here we have the water. So water mass is 1 gram and whose volume is 1 centimeter cube. Now, so this is converted to steam of volume, so 1671 centimeter cube. So this is a final volume, this is V1, so let it be, this is V2, this one, let it be V1 is equals to 1 centimeter cube. Fine. Chalo. So then at under the normal atmospheric pressure, so the pressure is equal to the PATM, atmospheric pressure, which is constant, 10 to the power 5 Pascal. So this is the constant term, the pressure is constant. Chalo. So every sentence and every word has meaning in this question. Okay, you guys have to understand each statement properly, right? Chalo. So then, so the steam formed 1671 centimeter cube if the specific heat of the vaporization is given. So L of V is given as 2256 joule per gram. So the first thing I have to find the change in internal energy. Sir, here that there is no temperature change, 100 degrees at the same temperature. So delta T 0. So can we consider the internal energy 0? So if there is no temperature change at under same temperature, so can we consider internal energy is 0? Delta U is equals to, you know that this is a formula. So delta T 0, delta U will be 0. But the thing is, it's not the ideal gas given. That formula is only valid for the ideal gases, right? So here it is not the ideal gas. So what we have to do then? So I'll find, so the heat first. So the delta Q is equals to, shall I use the latent heat formula, ml, right? So what is the mass? So mass of this one is 1 gram, right? So yeah, 1 gram into, so 2256 joule per gram. So let it be in grams only, 2256 we got. This is a delta Q, right? Chal. So then, shall I find the work done so that I can find the internal energy? So here the pressure is constant, volume is changing. So can I use this formula to find the work done? The work done is equals to P into delta V. So what's the pressure? 10 to the power 5 into, so what's the volume? So the volume is, the delta V is equals to 1671 minus 1, which is 1670 centimeter cube, right? But here it is in pascals or Newton per meter square. So convert this to 1670 into 10 to the power minus 6, let's write, right? So 1670 into 10 to the power minus 6. So do one thing. So here 0, here 0, here 10 to the power minus 6 gets cancelled. 10 to the power 5 into 10. So which is nothing but 10 to the power 6, and 10 to the power minus 6 gets cancelled. So we got the work done is equals to 167 done joules. So this is also joules. So now what do we need? So we need the internal energy, right? So again use the first law of thermodynamics. So the what's the first law of thermodynamics is, so the delta Q is equals to W plus delta U. So from here delta U is equals to delta Q minus W. So what is delta Q? 2256 minus 167. So this comes out to be 167 means 33. Okay, so 33. 33, if you add this one, I could see the closest option is 2089. I'll go according to the options. Yeah, so 2089. So if I add the 167 for that, so 240, yes, so 256, yes. So this is the correct answer, 2089. Done? Clear, guys? Understood everyone this question? Getting simple process. Chalo, so try this question on your own. A sample of 0.1 gram of water at 100 degrees and normal pressure, so 1.013 into 10 to the power 5. So you can consider it as 10 to the power 5 Newton per meter square, or 10 to the power 5 pascals. Requires 54 calorie of heat energy to convert to steam at 100 degrees centigrade. See here, again the temperature is constant, but the sample is not the ideal gas. It's a 0.1 gram of water. Clear? So they are asking change in internal energy. So same previous concept. So but don't use delta T 0, delta U also will be 0. There is no 0 option at all, first of all. Even if they give also, you should not choose, because it's not the ideal gas, right? So same procedure, what I will do, there is 0.1 gram of water. So this is water which is of 0.1 gram. So then which is at 100 degrees centigrade. Now it is converted to steam. So at the same pressure, so the PATM, which is equals to approximately, I am taking 10 to the power 5 Newton per meter square or 10 to the power 5 Pascal. So it requires how much heat? Heat also they gave. So previously they gave the hint. So here they directly gave the heat formula, heat value. So 54 calories. Done. So to convert to steam at 100 degrees centigrade, here it is at 100 degrees centigrade. So if the volume of the steam required produced is 161.1 cc, so which is nothing but, so the V2 is equals to 160.1 centimeter cube. So here it is 0.1 gram means 0.1 cc. V1 is 0.1 centimeter cube. So the pressure is constant atmospheric pressure. So first the heat delta Q we know. What is the delta Q? 54 calorie. Convert it to joules, guys. So calorie to joule, multiply it with 54 into 4.2. So how much we get this one? So 54 into 4.2. So we get 8. So 10. So here 16, 20, 21. So which is 8, 6, 2, 2. So 2 to 6.8 joules. So done? Yes. So now let's go for the heat we got. So can we find the work done? So what's the work done? The pressure is constant. So it is the normal pressure, the atmospheric pressure. Pressure is not changing. So to find the work done, shall I use this formula? P into the delta V. So what's our pressure? So I am taking 10 to the power 5 Newton per meter square. So here the volume change, the change in the volume is V2 minus V1, 167.1 minus 0.1, which is 167 centimeter cube. So I am writing it as, so 10 to the power minus 6 meter cube. So substitute it here. So 167 into 10 to the power minus 6. So here 1 gets cancelled. So we have 10 to the power minus 1, which is nothing but 16.7 joules. Right? Clear only? This is delta V is centimeter cube only, right? So 167, correct na? So yes, 157 into 10 to the power minus 6. So this one is what? Pressure is 1.013 into 10 to the power 5. Okay. So here 10 to the power minus 1 will be left. So 16.7. Yes, fine. So then I have just use this concept. So the work, according to the first law, the delta Q is equals to W plus delta U. So I need the internal energy, change in internal energy, right? So that the internal energy delta U is equals to delta Q minus W. So what is delta Q? 226.8 minus this one is 16.7. So if you subtract 16, so it will be 212, right? Not 212. So 210 approximately. So 210, the closest option I will go for 208 approximately. So this is 210.1 joules. So the closest option I can choose because the options are bit far, right? So option 2 is a correct one, guys. Understood? You should understand the procedure first. Okay, chala. So done. Next, what do we have? So we have different types of processes in thermodynamics. So hope you have already studied the chemistry, but here what are all the key points that you have to remember? So and how the questions will be framed. So there will focus more. Okay, I am not going for any kind of derivations. So isobaric first. Isobaric means the constant pressure. The constant pressure, right? So there is no change in the pressure. So that means delta P 0. So the constant pressure, so which is delta P 0. Sorry guys. And then so isochoric. So constant volume. Isochoric, so it's a constant volume. So which is nothing but, so delta V 0. Done. So isothermal, so constant temperature. So which is delta T 0. Adiabatic, so there is no heat exchange between the surroundings and the system. So no heat exchange. So no heat exchange between system and surroundings, between system and surroundings. Alright, chalo. So here the delta Q is equals to 0. Done. Chalo. So let's move further. So just note this one. So we'll discuss one by one in detail. Okay. Chalo. So first let's go for the isobaric process. So as I discussed here earlier, so the pressure is going to be constant. So now in this context, in the isobaric process, actually the Charles law is applicable. The Charles law is applicable. So Charles law, what it says, see, so you know the ideal gas equation, remember this ideal gas equation, PV is equals to nRT. So if the pressure is constant, N is constant already, T is R is constant, so the volume will be directly proportional to temperature, so the V will be directly proportional to T. Shall I say this? So that means, so the V is equals to, I can write some constant into T, right? Chalo. So here I can write, so the V by T is equals to K. Yes, chalo. And then, so the V1 by T1 is equals to V2 by T2. So shall we write? So we can go for this, right? Yes. So always remember this ideal gas equation. If it's the isobaric process, the pressure is going to be constant and NR always constant. So the volume is directly proportional to temperature. So if it's an isochoric process, volume is going to be constant and N and R are already constant. So pressure will be directly proportional to temperature in isochoric process. Right? So we'll discuss that. No problem. So this part you understood? This part is clear. So now let's go for the graphs. Let's go for the graphs. So first let's draw the volume versus temperature graph. So VT, PT, PV graphs you have to draw. So first let me draw. So the V versus T. V versus T. So how they both are? V is directly proportional to T. So if V is directly proportional to T, so can we use this graph directly? So as the temperature increases, the volume is also increases. So the V versus T. So and what is the slope of this one? What is the slope? The slope is equals to dV by dt. The slope is equals to dV by dt. Shall we write this? dV by dt. So now if you observe the ideal gas equation, PV is equals to nRT. So now if I differentiate either side, so the P is already constant in isobaric process, the pressure is constant. So now P outside, so I'll write dV is equals to nR are the constants. So then I'll write dt. Then so shall I write, so the dV by, so the dt, bring this dV by dt is equals to nR by P. nR by P. So dV by dt is equals to nR by P. So here the dV by dt is equals to, I can write nR by P. Done. Understood guys? Chal. So this is a first graph. So then I can go for, so the VT graph over, so you can go for PT and PV graphs. So shall I do it in the next slide? Let me take the same template. Just note the points in the sequence. Okay, chal. So then I'll go for PT graph. So the pressure versus temperature. So as the temperature increases, what happens to the pressure? So the pressure remains constant. So the pressure is going to be constant like this. So this is in the case of expansion, the pressure. Right. So whereas, so here the pressure is constant, right? So the pressure is constant means pressure will not change. So that is as with respect to the temperature. So the pressure is going to be constant like this. This is a P versus T curve. So PV curve we have seen. VT curve we have seen, and then PT curve we have seen. Let's see PV curve also. Here, so what's a PV curve? So as the volume increases, the pressure is going to be constant. This is in the case of expansion. Now, so this is in the case of compression. Done. So the slope will be, if it is a horizontal line, the slope will be 0, right? So you can write, so the dp by dt, so which is the slope, which is equals to 0. And then here, so the slope which is dp by dv, which is equals to 0 in this case again. Clear guys? Understood the graphs? Chalo. So just have a look at them. Just have a look at them. We'll move further. Done? Chalo. Next. So the next important points. So shall we do it in the next slide? Yes, better. So let's go for the molar specific heat capacity in isobaric process. So the molar specific heat capacity in isobaric process. So what is molar specific heat capacity? So the CV in CP in constant pressure case, right? So actually what is it? What its formula? Let's write first C. So the molar specific heat capacity formula. So it's a delta Q or Q by N delta T. Q by N delta T. Right? So now at constant pressure, shall I write? So the delta Q at constant pressure by N delta T. Yes or no? So the molar specific heat capacity at constant pressure Cp is equals to Qp by N delta T. That's it. Understood? So then what happens to the internal energy and what happens to the heat? So let's write. So the heat in this case and the internal energy, you write the formulas. And then all these things we are going to analyze for the different processes. I am just writing the sequence. Now tell me, what is the molar specific heat capacity for the isobaric process? So what's the formula for Cp? This is for Cp, or you can also write this Cp in terms of degrees of freedom. What is the degrees of freedom? F by 2 plus 1 into R. R. You can also write it in terms of the gamma. Did you guys remember the last class? Gamma R by gamma minus 1. I'll go a bit slow. So just understand the concepts carefully. So the first, the molar specific heat capacity is delta Q by N delta T at the constant pressure. So it's going to be, so the heat absorbed at the constant pressure by N delta T, right? So the Cp formula you can also write in terms of the degrees of freedom. You can also write in terms of the gamma. Yes. Chal. So now what is the heat in constant pressure? Let's say in the constant pressure means I am talking about the isobaric process. So in the isobaric process, so the delta Qp, so which is equals to, you can write it from here. So N Cp, this is Cp, right, in isobaric process. So N Cp delta T. Just we are deriving one from the another, that's it. So N Cp delta T here. So N into, so what is Cp? Cp you can write either F by 2 plus 1 into R. R. So in the same into delta T is there. Into delta T. So is equals to R. In place of Cp you can substitute the gamma value also. So N into, so in place of Cp I will write gamma R by gamma minus 1 into delta T. That's it. Done? Clear everyone? Is it clear? Is this part clear? Chalo. So note this down. And so for the internal energy we have only one formula. So what's the internal energy formula? So the delta U is equals to N into R, F by 2 into N R delta T. R, you can also write N into, so this F by 2 R is nothing but CV into delta T. N CV delta T. N, this F by 2 into R is CV into delta T only. Clear? Understood this part? NCV delta T. So these are all the formulas. So now let's go for the work done formula. So the actual, remember the actual formula of the work done in thermodynamics is, so the integration of PdV. Integration of PdV, right? So which means, so shall I write, so the pressure is constant in the isobaric process. Yes, chalo. So the integration of dV. So let's say the volume is changing from V1 to V2. So the pressure P, it's going to be, so V2 minus V1. So this is P delta V in the isobaric process. So chalo, so note these things down, important guys. So we'll go for another important relation, just write them aside. In the class only you guys should learn this. Done? Chalo. Done? See, just a minute guys. So here, in place of this P delta V, you can also write, see, PV is equals to nRT. Right? So if it is the constant pressure, if I differentiate it on either side, so P into delta V is equals to NR is the constant, NR into delta T. So in place of this PV, P delta V, you can also write NR delta T. So that's also possible. Clear, everyone? So let's go for one more important relation in the isobaric process. So direct they'll ask the question, isobaric process. In isobaric process, find the ratio of delta Q to W to delta U. So the delta Q to W to delta U. So in terms of gamma and in terms of degrees of freedom. So first let's say in terms of degrees of freedom we'll write. In terms of degrees of freedom. In terms of degree of freedom, F. So understand carefully. So what is delta Q formula? The heat. Delta Q formula is in isobaric process we are discussing. NCP delta T. This is done. So work done P delta V. Chalo. So the delta U, there is only one formula, NCV delta T. Chalo. So now I need in terms of the degrees of freedom. So what I am doing is, so N into, in place of Cp, let me write F by 2 plus 1 into R into delta T. Chalo. So then, so here P into, so the delta V, let it be. So P into delta V, let it be. So then here, or else let's write in place of P, here let's write NR delta T. We can use, right, NR delta T. Chalo. So next, so NCV delta T, N into, so in place of CV, I'll use F by 2R in degree, in terms of degrees of freedom. So into delta T. Done. Chalo. So I can cancel NR delta T, NR delta T, NR delta T. So here it's going to be F by 2 plus 1 is to, so 1 is to, so F by 2. Done. So this is the relation in terms of degrees of freedom. So if they ask for the monoatomic gas, you'll substitute the F value is equals to 3. If they ask for some diatomic gas, so you'll write it for the F is equals to 5. If for triatomic gas, you take F value as 6. So sometimes they might ask in the isobaric process, so the delta Q by W, so take this as a homework. I'll give different questions as a homework. So just take this one. So the question is, so find delta Q by W ratio for diatomic gas at constant pressure. At constant pressure. So the question can be framed any way. Okay. So and this is the question 2. Let's say. So find delta Q by delta U ratio for monoatomic gas at constant pressure. Monoatomic gas at constant pressure. Or, so the question can be framed this way. So the Q3, question 3, find, so delta U is to W is to delta Q for triatomic gas at constant pressure. At constant pressure. So you know the values, the F values for the diatomic, for the monoatomic, for the triatomic, and you know the ratio, right? So you can just simply substitute at constant pressure. This whole slide is a homework for you. I am not going to do this in the class, so you guys have to do. I already derived this one. Chalo, so note this down first. Done. Chal. Sir, can we write in terms of the degrees of gamma? Yes, we can write it in terms of the gamma also. So in the isobaric process, so let's write the ratio of W to Q to U, delta U. So W, work done, 2, so the heat 2, so the internal energy. So let's write in terms of gamma. In terms of gamma. Chalo. So in terms of gamma, W. So we can write what's the formula for the at constant pressure. Isobaric means at constant pressure. So the work done formula is P delta V. Chalo. So the Q, NC P delta T. Understand the procedure first. So and for internal energy we have only one formula. So that is NCV delta T. Chalo. So now I need in terms of gamma. So I can't write P in terms of gamma. I can't write delta V in terms of gamma. So let's write NR delta T. The only thing I can do for the work is this one. Right? Chalo. So N into what is Cp? At constant pressure in terms of gamma. So which is nothing but gamma R by gamma minus 1 into delta T. Did you guys remember yesterday's class? Right? Chalo. So into N into, so this is gamma R by gamma minus 1. R by gamma minus 1 into delta T. That's it. So NR delta T, NR delta T, NR delta T cancel. So here 1 is to, so this comes out to be, we have gamma by gamma minus 1. So and then, so here it is 1 by gamma minus 1. That's it. So if they ask for the monoatomic gas, diatomic gas or triatomic gas, you know the gamma values. So the gamma for the monoatomic gas is 1.67 and gamma for the diatomic gas is 1.4. So the gamma for the triatomic gas is 1.33, right? So you know these values. You can simply substitute and get the final answer. Understood? 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 So just have a look at the isobaric process. So in the first slide, so in the isobaric process, the Charles law. So the V is directly proportional to T, and then V1 by T1 is equals to V2 by T2. So how to remember? Pressure is constant, V is directly proportional to T. So remember the ideal gas equation. So then we drew the graphs. So V versus T, P versus T, so P versus V. So and we calculated slopes. So this one is also important. Remember this, dV by dt, the slope of VT curve, so will be equals to tan theta, so which is also equals to NR by P. So the question can be framed directly based on this, right? Chalo. And then, so graphs done. And then, so the molar specific heat capacity in isobaric process, the heat absorbed or released in the isobaric process, and internal energy in the isobaric process, the work done in the isobaric process, and their ratios in terms of the degrees of freedom and their ratios in terms of the gamma. Clear? Understood, guys? So chalo, next. So can you guys solve the questions now? So this question you can solve it easily. The same as the question I gave it as a homework. Heat is supplied to a diatomic gas at constant pressure. For which gas? For the diatomic gas. F is equals to what? For the diatomic gas, F is equals to 5. So then the ratio of delta Q to delta Q to delta U to W. So they can ask any twisted way. Delta U is to W is to delta Q, or delta Q by delta Q by W, or delta U by W, or W by delta U, or delta Q by delta U. Anything they can ask. Just you have to remember the formulas, concept. That's it. Okay. So let me go for the procedure again. I need in terms of the degrees of freedom because they mentioned diatomic gas. So even if you want, you can go for the gamma, but that's going to be decimals, so no need to go for that. So directly let's go for the delta Q in terms of degrees of freedom. So here I know NCP delta T, yes. So here I know NCV delta T, yes. So here W P into delta V, yes. So then, so here I can write N into in terms of degrees of freedom. So Cp is F by 2 plus 1 into R delta T, yes. So N into Cv, F by 2 into R into delta V, yes. So here NR delta T, yes. Chalo. So NR delta T, NR delta T, NR delta T cancel. F by 2 plus 1 here, F by 2 here, 1. So here, so we wrote it in the order only, right? Yes. So then for the diatomic gas, substitute. So we get 5 by 2 plus 1. So which is 7 by 2 is to. So here 5 by 2 is to. Here 1. So multiply it with 2. So that 7 is to 5 is to 2 is the correct answer. Multiply everything with 2. So 7 is to 5 is to 2. So option 3 is the correct one, guys. Any difficulty? Nothing. Right? Chalo. So for an ideal diatomic gas, is heated at constant pressure. So the fraction of heat energy which increases the internal energy, the fraction of heat energy which increases the internal energy. So that means delta Q by delta U you have to calculate. So can you guys do that? Delta Q by delta U for which one? For the diatomic gas. F is equals to 5. So I will just stand aside, calculate it on your own. So you have to find delta Q by delta U. The fraction of heat, the fraction of energy, oh sorry, reverse. The fraction of heat energy which increases the internal energy, right? Delta U by delta Q. Oh, this you have to calculate. Done. For the diatomic gas, just now we know the relation. Delta U by delta Q, I'll directly write delta U by delta Q. F by 2 by F by 2 plus 1. So I'll directly go for the formula. F by 2 by F by 2 plus 1. So substitute the value now. So F is 5 by 2 by 5 by 2 plus 1 is 7 by 2. So 2 cancel. I'll directly write the answer as 5 by 7. Option 4. Done, guys? Clear? Chalo, good. So then we have one more question. So the volume of a monoatomic gas varies with temperature. V is directly proportional to T as shown in the figure. So you can see V is directly proportional to the T linear graph. So the ratio of work done by the gas to heat absorbed by it. So the ratio of undergoes a state from A to B. So what they are asking? So it's a monoatomic gas. So they are asking the ratio of work done W by, so the heat absorbed delta Q in terms of degrees of freedom. So W by delta Q. So W by delta Q. W by delta Q, which is 1 by F by 2 plus 1. Right? So 1 by F by 2 plus 1. So it's a monoatomic gas. 1 by 3 by 2 plus 1. So which is 1 by, so this is 5 by 2. So 2 will go up, which is 2 by 5. 2 by 5. Option A is the correct answer. Hope you guys understood now. Clear? Chal. So this, can you take it as a homework? The ratio of specific heats of gas at constant pressure they gave to that the constant volume. So what's that given? C at constant pressure to constant value is gamma. Cp by Cv is gamma. We know that. The change in internal energy of the given mass of the gas when the volume changes from V2 to V at constant pressure P. So at constant pressure, what is the change in internal energy they are asking. So what's the change in internal energy in terms of gamma we required? So the change in internal energy, we have only one formula. What is that? NCV delta T, guys. Right. So now we need it in terms of the gamma. So N into what is CV in terms of gamma? R by gamma minus 1. R by gamma minus 1. Yes or no? So then shall I use, I need the pressure. So NR delta T, shall I use, pressure is constant. So P delta V by gamma minus 1. So P delta V by gamma minus 1, which is PV by gamma minus 1. Option 3. Done. For the internal energy, we have only one formula that is there. So here they gave the, further you can choose this one also, P into V2 minus V1 by gamma minus 1. In the question they said volume is changing from V2 to V. So P into what is V2 to V minus V by gamma minus 1, which is PV by gamma minus 1. PV by gamma minus 1. Option 3. Done. Clear, everyone? So let's move further. So now let's go for the isochoric process. So isochoric process means constant volume. Same concepts let's discuss. Whatever we dealt there, so same thing we are going to do here. So here isochoric process means volume constant. PV is equals to nRT. So if the volume is constant, NR is already constant. So the pressure is directly proportional to T. The P is directly proportional to T. Yes or no? So that means, so the P by T is going to be constant. The P by T is going to be constant. So which means P1 by T1 is equals to P2 by T2. That's it. P1 by T1 is equals to P2 by T2. So then draw the graphs. So which graphs we have to draw? You guys already know. So let me give the. So first let's draw the P versus T curve. Then so P versus V. Then P versus V. So chalo, so you guys draw these graphs. I'll just stand aside. Draw these graphs first. Done. So first P versus T. So P versus T is a straight line. Done. So then, so here the slope is going to be theta. So the slope is equals to, so which we can write, so tan theta, which is equals to, so the dP by dt. So you can also do one thing. So the PV is equals to nRT, right, for a ideal gas, right? Chalo. So I can write, so at volume is constant, so V into dP, NR is constant, NR dt. So then I can write the dP by dt is equals to, so dP by dt is equals to NR by V. So I can also write this as NR by V. Simple thing, right? Chal. Next. So the pressure versus volume. So the volume should be constant and the pressure changes like this. Here, like this. Right? Chalo. So as the pressure increases or the pressure decreases. Right? So then here the slope is infinity tan 90, which is nothing but slope is going to be infinity. So what about here? So the volume should be constant and, sorry, again pressure I wrote. This is pressure, pressure versus temperature, volume versus temperature. As the temperature increases, volume should be constant. So volume should be constant and, sorry, let's write this way. So volume versus the temperature. So the volume should be constant with the temperature. Then, so here the dV by dt, the slope is dV by dt, which is 0. Horizontal line, right? The slope is 0. Understood this part, guys? Chalo. So next, what we have to do? So what is the molar specific heat capacity? Molar specific heat capacity in isochoric process. You guys have to do now. So molar specific heat capacity in isochoric process. So then heat in isochoric process. So then, so internal energy in isochoric process. Then the work done in isochoric process. Chalo. So let's try this, guys. Try it on your own. Everyone, first try this concept on your own. Already we discussed it for the isobaric process, right? So isochoric process means CV. So CV is equals to, what's the formula that we know? CV is equals to F by 2R. Yes. And then in terms of gamma, you know that R by gamma minus 1. Yes, sir. So this is easy. So leave about the molar specific heat capacity now. So come to the heat. So the heat at constant volume delta QV is equals to NCV delta T. Heat at constant pressure is QP, which is NCP delta T. So heat at constant volume is NCV delta T. So N into what is CV? CV is either F by 2 R. So in terms of gamma, if we have to write R by gamma minus 1 in terms of CV. So into delta T. So that also we can use. Clear? And then, so what about internal energy? For the internal energy, only one formula. So what is that? NCV delta T. So which is nothing but N into, in place of CV, you can write it in degrees of freedom. So N F by 2 R delta T, or N R by gamma minus 1 into delta T. So now what is the work done? So the only formula that we know for the work done is, so the integration of P1 to, the integration of P dV. So the integration of P dV. So but here the volume is the volume is constant. So if the volume is constant, so what happens to the work done? V1 to V2. So the volume is constant, right? So then the work done will be 0. Done. So this is for the isochoric process. Hope you guys understood this part. Done? Chala. So next, let's go for the isothermal process. Important. So here the temperature is constant. Here the temperature is going to be constant. Chala. So if the temperature is constant, let's have a look at the ideal gas equation. PV is equals to nRT. PV is equals to nRT. N is constant, R is constant, T is constant. So that means PV is going to be constant. So I can write in the isothermal process, so the PV is going to be constant. So which is nothing but P is inversely proportional to V. I can write, if the pressure increases, volume decreases. If the volume decreases, pressure increases. Right? So this is a Boyle's law. In the gas laws of chemistry, you might have studied already this one. So this is the gas law. Sorry, Boyle's law. Done. Chalo. So here, what we can write? So the PV is constant. So that P1 V1 is equals to P2 V2. P1 V1 is equals to P2 V2. So this is the basic information. Now let's go for the graphs. Same sequence, follow the same sequence what we did for the other processes. So here, first let me draw an important graph of P versus V. So let's talk about this graph. So this is P versus V. So the P is inversely proportional to V. So then, like this, the graph comes out to be somewhat like this. Yes or no? So the P is inversely proportional to V. So this is called the isotherm at constant temperature. So this is called the isotherm. Okay. So here the dp, so what's that? This is p versus v curve, right? So here the dp by dv is going to be the slope, which is equals to the tan theta. The dp by dv is going to be the slope, which is equals to, so the tan theta. So here actually the pv is constant. Here the pv is constant. So now if you do the integration, pv is equals to nRT. PV is equals to nRT. So where PV is a constant. So now let's differentiate this on either side. Let's differentiate this on either side. So P make it constant one time and V make it constant one time. So that however this whole thing is going to be constant. Yes or no? So then I can write the pressure varying and volume is varying. So then what do you get? P into dV plus P dV, or else let's write the constant here. So the differentiation of constant is 0. So P dV plus V dP is equals to 0. So the differentiation of UV method, product rule, you already know. So from here, so the P dV is equals to minus V dP. So from here I need the dP by dV. So the dP by dV. So bring this to this side. So which we get, so the dP by dV. So you brought it to this side. So this one minus P by V. Understood? The slope of this one is minus P by V. Understood this part, guys? So just have a look at that one. Done. Done. Chal. Important. So here the slope is the dV by dP is equals to the slope, which is equals to the tan theta, which is equals to minus v, P by V. Done? Chalo. So here at constant temperature the P versus V curve is called the isotherm, as I mentioned earlier. So let's discuss more about this graph. So the P versus V. So let's say if I take at some temperature here, so this is a temperature T1, so this is the isotherm that we got. Now, so if I take at some different temperature, let's suppose, so the T2 temperature, let it be greater than the T1. So then the isotherm will be, its slope will be more nR into T, right? PV is equals to nR into T. So if the temperature increases, so the nR into T, the nRT value increases, which is nothing but the PV value increases. So the curve will be like this. This is for T2. So if the temperature T3 is greater than T1, so then the isotherm will be somewhat like this. So this is at temperature T2. So then this is at some temperature T3, right? So and then if I take some temperature T0, so which is like this, so then this is a T0 isotherm. Understood? Clear everyone? Chalo. So note this point. So this is the P versus V curve. Now, so let's go for so can you draw the P versus T curve and V versus T curve? So you guys draw it. V versus T curve and the P versus T curve. Draw it first. Quickly. Simple one, simple one. As the temperature increases, what happens to the volume? Thermal, right? The temperature constant, sorry. Right? So here the slope is, dV by dt, which is infinity. Here also the slope is dP by dt, which is infinity. Done? Chalo. Now let's go for the next one. So now the different terms like the molar specific heat capacity, and then so the heat delta Q at constant temperature, and then the internal energy at constant temperature, and then so the work done at the constant temperature. Chalo, so let's fill this slide. You guys have to try it on your own. Already I did it for 2 processes slide, right? So you have to do it on your own now. So first thing, so what happens to the molar specific heat capacity? So the C is equals to delta Q by N delta T, actual formula. So here there is no change in temperature. So the delta T is 0. So if the delta T is 0, so the C will become infinity. So the molar specific heat capacity, it becomes infinity, right? So then what about the what's that heat? So the heat will be, so which is N CV delta T at not NCV. So the delta T is equals to 0. If you take any process, the heat is also going to be 0. Yes or no? Or else let's take out the heat term. So we'll talk about it later. So then, so the work done, we will talk about the heat here. So then internal energy first. So NCV delta T. So where? So delta T is 0. So the internal energy will be 0. And the molar specific heat capacity is infinity. So then what about the work done? The work done actual formula is PdV. Now, so let's write the from where to where? From V1 to V2. So write it from V1 to V2. V1 to V2. Differentiate it. So how can you write? In place of P, so what you do is write, let's use some ideal gas formula. So the PV is equals to nRT, right? So the derivation I am not going for that. So but simply you can write PV is equals to nRT by V. So if you substitute that nRT by V here, so then it comes out to be nRT common. So V dV, nRTV common. So then by here integration of, so V1 to V2. So here it comes out to be dV by V. So which is nothing but nRT. So log E. So we get, so the V2 by V1 R. So nRT. So we can also write this as log E. So the pressure is inversely proportional to volume, right? So that's why P1 by P2. V2 by V1 means I can write P1 by P2. So we know here, right? So we have already studied P1 V1 is equals to P2 V2. So the P1 by P2 is equals to V2 by V1, right? So the same thing I substituted here. Done. So at constant pressure, so the work done, not pressure, at constant temperature, the work done will be equals to, so this one, nRT log E V2 by V1. Note this down, everyone. First. Clear? So this you can also write it. This you can also write it. So the work done in isothermal as what's that? nRT log E either V2 by V1 or so nRT log E P1 by P2, or you can also write that. So take out the log E. So put the base log 10. So which is 2.303 log nRT log base 10. So V2 by V1 R. So we can also write it as, so 2.303 nRT log base 10. So P1 by P2. Clear? So this is all about the work done in the isothermal process. So just the conversions. You guys have to remember this part. Done. So now let's come to the heat part. So now apply the first law of thermodynamics to find out the heat. So apply the work done. First law of thermodynamics. So what's the heat formula? The delta Q is equals to W plus delta U. Right. Chal. So in the isothermal process, the delta U is 0. Just now we have discussed. So the isothermal process, so the delta U is going to be 0. So then, so what about the delta Q? So the delta Q will be equals to work done. That's what I have said in the previous slide. Right. So I skipped the heat here. So then we did it here according to the first law of thermodynamics. Chalo. So note this down. First, hope you guys are understanding. Right. So you can also write it. The heat also equals to nRT log E. So V2 by V1 R. So which is also nRT log E P1 by P2, or you can write it in terms of log base 10. So these formulas also you can write it there. So the heat and work will be same. Chalo. So then what else we left? So we got a question. So 1 mole of an ideal gas goes from an initial state A to final state B via 2 processes. It first undergoes isothermal expansion from V to 3V. Isothermal expansion. Isothermal means the temperature. So V to 3V. So the P versus V curve if you draw, isothermal means V to 3V. So this is V, and then this is going to be obviously 3V. Done. Chal. So this is one curve. P, this is one. And then what else is there next? And then its volume is reduced from 3V to V at constant pressure. So 3V to P, 3V to V at constant pressure. Constant pressure means the pressure is constant like this, and this is the first one like this and the second one like this. So here the direction is given wrong. So here, so slant, here, so not straight, here, yes, option 4 is the correct one. See here, from A to this, here to here, isothermal expansion, from here to here, the isobaric compression at constant pressure. Done. Clear? So let's move further. So what else we have? So we got one more question. So can you guys take this question? 5 moles of an ideal gas is compressed from 2V to V isothermally. So at T Kelvin. So find the work done in the process. So the work done is equals to, so in terms of log E is there. So I can use the formula nRT log E. So in terms of volume is V2 by V1. Done. So number of moles are 5 moles. So 5 RT into log E. So which is V2 is 2V by V. So V 2V to V. Final is V, right? Final is V. So initial is 2V. Fine. So 5 RT into log E. So V cancel 1 by 2. So let's do further. So 5 RT. So log E. So I can write this as 2 to the power minus 1. So log properties you know, right? So that minus 1 power will come out. So minus 5 RT. So log E 2. So if it is given in log base 10, so multiply it with 2.303. So here it is. So 2 options are there. Take care of the sign also. Option 2 is the correct one, guys. Done. Clear? So then adiabatic process. So adiabatic process, there is no heat exchange. So the delta Q is 0. So no heat exchange between the system and surroundings. Okay. So in adiabatic processes, so the PV to the power gamma is taken as constant. Remember this one. So in adiabatic processes, you have to remember from now. So the PV to the power gamma is going to be constant. So you can also do it in the different ways, like, so the P1 V1 to the power gamma is equals to P2 V2 to the power gamma is also is possible, right? So or else, so you can also write it as, so the P in place of P, we know that PV is equals to nRT, right? So in place of P, you can write nRT by V, or in place of V, you can write nRT by P. So you can substitute that and get the one more formula. So how, sir? See here. So here I can write, so in place of P, so what we can write, nRT by V, nRT by V in place of P, so into V to the power gamma, so which is equals to constant. So that I get here, so what we can write here, so if you send it to that side, nRT V to the power gamma minus 1 is equals to constant. That's it. Understood this part? So nRT V to the power gamma is equals to constant. Or you can also do this way. So in place of PV to the power gamma is actually is equals to constant, right? So then I can write here P, let it be, in place of V, so we'll write, so nRT by P to the power gamma is equals to constant. So let's do one thing. So P into, so here P to the power gamma, if I send it to P to the power 1 minus gamma, so into nRT to the power gamma is going to be constant again. That's it. These are the different ways you can write it in the adiabatic process. Clear? So if the temperature is changing there, so you can write according to the temperature. So nR you can see, you can also write it as nR, you can send it to that side. So T into V to the power minus 1 gamma is equals to constant here also. So the T to the power gamma into P to the power 1 minus gamma is equals to constant. Understanding? Clear everyone? Just the basic things whatever we are discussing here, so you guys have to remember them. Okay, so follow the sequence, that's it. So many formulas are coming, I know, but you guys have to follow the procedure and write these formulas, all the formulas at one place, and do revise them daily. Chalo. So now have a look at this slide. So we'll go for the graph now. So the P versus V curve is important here. So what's a P versus V curve? Again, it's so this is the P versus V curve. So it is also the same this way, but the slope is more. Okay, so the PV to the power gamma is again the constant. So but the slope of PV, see adiabatic process and isothermal, so here the graphs, PV graphs will be same. So if they both mention, let's say, so if I take, so the two curves here, so the P versus V, so I can write here, so consider, let's suppose this is the one and this is one more curve. So now identify, let's say this is the first one, let's say this is the second one. Identify which is the isothermal and which is the adiabatic slope. So wherever the slope is more, so the slope of the adiabatic curve is more than the slope of the adiabatic will be more than that of the slope of the isothermal. Slope of isothermal. Clear? So that means the dP by dV of adiabatic will be greater than that of the dP by dV of isothermal. dP by dV of the isothermal. Remember this, guys. So here the first one is slope is more, the second one the slope is less. This is rapidly falling. So here the first one is a adiabatic curve and the second one we can say it as a isothermal. Clear? So actually the adiabatic slope will be gamma times that of the isothermal slope. Okay, so you can write that point also. Clear, guys? Chal. Done? Done? You can write that point also where I'll write here. So the slope of isothermal, you know, right? What is the isothermal slope? Minus P by V we got. Remembered? Minus P by V. dP by dV is equals to minus P by V got. So whereas the slope of the adiabatic will be gamma times that of the isothermal. Okay, so I'll write here the slope of adiabatic will be gamma times that of the slope of isothermal. Done, guys? Clear? Chalo. So hope this concept is done. Next. So anything is left? So the work done, the processes we did not see, right? Yeah. So what happens to the molar specific heat capacity? So you guys do this one. So the molar specific heat capacity, and then so the heat, we'll talk about it later. So the internal energy in the adiabatic process, the internal energy, and then do the work done. So we did not talk about this in adiabatic process. So let's try this now. Try it one by one. So the specific heat capacity, so delta Q by N delta T. So here there is no heat exchange. Yes or no? So C is equals to, we know that, so delta Q by N delta T. So here there is no heat exchange in the adiabatic process. So that's why numerator part is 0. So the whole denominator will become 0. So then if the delta Q is 0, so the heat, we can write it here. Yes, heat, write it here itself. So the heat is nothing but delta Q. There is no heat exchange. Delta Q is equals to 0. So what about internal energy? So we have the internal energy delta U, only the one formula, which is NCV delta T. NCV delta T, or N into, so F by 2 R delta T, or so N into R by gamma minus 1 into delta T. That's it. So the work done actual formula we have, so the P dV. So here he had to do some changes. So what's the work done here? What's the work done here? So the work done is equals to, so according to the let's come, instead of this one, let's come from the first law of thermodynamics. Easiest one. See, this is again the confusing one. So the work done, what I'll do is, I know the heat, I know the internal energy. So shall I use this formula? So the delta Q is equals to work done plus the change in internal energy. So here in the adiabatic process, delta Q is 0. So which is nothing but, so W plus delta U. So here the work done will be equals to minus the change in internal energy. That's it. See, here the internal energy is changing. Let's suppose if I write NR delta T is nothing but T2 minus T1 by gamma minus 1. So here NR T2 minus NR T1 I can write by gamma minus 1. So which we can also write it as P2 V2 minus P1 V1 by gamma minus 1. So that you can substitute it here. So the work done is equals to negative of the internal energy. So you can substitute it over here. Done. Clear, everyone? Is this part clear? Clear. Done. Chalo. So this is what you have to remember. Chalo. So what you do is you summarize all the processes at one place and then write the formulas. Okay. So in which of the following process heat is neither absorbed nor released? Adiabatic, right? Chalo. So we consider a thermodynamic system. Delta U represents an increase in its internal energy. So work done by the system. So which of the following statements is true? Delta U is equals to minus W in adiabatic process. Yes. Delta U is equals to W in isothermal. No. So see, if you see the isothermal, delta U is not equals to W, right? Where is that? Delta U is not equals to W. Delta Q is equals to W in isothermal process, right? So that's why this statement is wrong here. So the second one, delta U is equals to minus W. No. So adiabatic process, delta U is equals to not W, it's a minus W. Option 1 is the correct one. Clear? Chal. So a monoatomic gas at pressure P1 and volume V1 is compressed adiabatically to 1/8 of its original volume. Find the final pressure. PV to the power gamma is equals to constant. You can use this. PV to the power gamma is equals to constant. So we can write adiabatic process P1 V1 to the power gamma is equals to P2 V2 to the power gamma. So then you have to find the initial pressure P1. So final pressure you have to find P2. So V1 is given and V2 is 1/8 of the original volume. So V2 is, so 1/8 of the V1. So can you guys take this as a homework? Simple concept, right? Chalo. So an ideal gas 27 degrees is compressed adiabatically to 8 by 27 of its original volume. So then the raise in temperature, in terms of temperature we required. So the T versus TV curve, TV you can use T to the power T into V to the power gamma minus 1 is equals to, here we can write T1 into V1 to the power gamma minus 1 is equals to T2 into V2 to the power gamma minus 1. Chalo. So you can use this in this question. So I'm just giving the hints, you guys can solve it easily. So take this as a homework 2. Chalo. So this question, the pressure again, the adiabatically, this also you can do. So here a diatomic gas, pressure of 2 atoms is compressed adiabatically so that its temperature rises. Pressure versus temperature. So PT, this equation you can use here. Which one? So PT. So T to the power gamma is equals to P to the power 1 minus gamma is equals to constant. Easy one again. So I'll write this also as homework for you. So this, where is it? This question is homework 3. Pressure, P, temperature, monatomic gas related by P. So again easy question. So homework 4. Homework 5 is a question. That's it. So 5 questions I gave it as a homework for you. Hope you guys understood the concepts. So the only thing that you have to do in heat and thermodynamics part is, so summarize each lecture after the class. Okay, so write all the formulas so that you will get the complete idea. Okay, believe in me. So now just sit for 10 minutes and write all the formulas. Just look at your class notes first for the next 5 minutes, then you start writing without seeing. Okay guys, chalo, we'll meet in the next lecture. So till then, keep studying. All the very best. Bye.